picking up where we left off last time, what this slide is talking about is something that I mentioned as I was going along, but I'll mention it again here. So when we have alkanes, the pictures that we've been looking at anyway, have always been just a chain of carbons, one attached to the other, but it doesn't have to be that simple structure. You can have what we call isomers of these different molecules. And what an isomer is it's a molecule where the number of atoms and the kind of atoms that are present is always the same, but the way that the molecule is arranged is different. So here it says let's draw 5 isomers of hexane. And actually I'm going to need to add in a slide there to do that. So one isomer of hexane would look like this. This is what we would call N-hexane. So the letter N, hexane. And this would have hydrogens just attached to everything so that the carbons all have their 4 bonds that they want. So that is N-hexane. If we wanted to get an isomer of this, all we would need to do is rearrange how those carbons are attached together. And by the way, for the rest of these that I'm going to draw here, I'm not going to put the hydrogens in. You can just trust me, or you can not trust me and check me. But the number of hydrogens is going to remain constant. So for the rest of these, I'm just going to draw how the carbons are attached together. And actually, I would encourage you to pause the video for a second and try to think of some different ways that these carbons could be arranged so that you would get a different molecule. And by the way, this is not a different molecule than this. Simply having them pointing in a different direction is not going to give you a different isomer. They have to be connected differently, not just pointing in a different direction. So while that is not an isomer, this is, because now the carbons are connected together differently. It's not just one long chain of carbons. It is one slightly shorter chain with a carbon in the middle. So go ahead and pause the video and see if you can come up with 3 more of the possible isomers of hexane. Alright, hopefully you gave an attempt at that. Let's see a few other isomers that we could possibly work with here. So this would be another possible isomer. We still have 6 carbons, but this is different than the previous 2 here. In addition, we could have this. That would be different. By the way, this is one isomer. This is not a different isomer. This is still the same isomer. Having the 2 carbons attached to this one is no different than having them attached to this one. Structurally speaking, all you did was take the molecule and flip it upside down. And if you can get the same molecule just by physically changing how you look at the molecule, then it's not a different isomer. It's still the same isomer. Alright, so let's see. There should be one more of these. Let me see if I can remember what it looks like. Let me see. If we do this, I don't think we're going to get anything different from that. So I don't think that is correct. So the reason why I say that's not going to give us anything different, because no matter where we put that last carbon, say we just put it there, well, now that's the same as this, but it's going to be the same thing no matter where we put that carbon. We're still just going to end up with the same thing as that. So having a carbon that is completely bonded to other carbons, that is not going to give us... oh, I know what to do. Yeah, okay. So that is different. So here we had 6 carbons in a line. Here we have 5 carbons in a line with a carbon attached to the middle carbon. Here we have 5 carbons in a line with a carbon attached to the second carbon in. And by the way, if we just say, well, what if we take this carbon and stick it on the end one? Well, then now you just have 6 carbons in a line again. Because again, we don't care about the orientation. We don't care about this versus this. Those two are exactly the same. It's just how you've drawn them is different. But in terms of the connectivity of the carbons, they are no different. So this is different than this because of where the carbon is attached. And then for these last two here, we have 4 carbons in a row where we have a carbon on each of the middle ones, and then both of the carbons on one of the middle ones. And so those are the 5 possible isomers of hexane. All right. And again, feel free to double check me to be sure. But if you put in all the hydrogens, so even on this one here where you say, well, but there's a carbon that has no hydrogens, you can't end up with the same number. Like, well, yeah, there's a carbon with no hydrogens, but there's also 4 carbons with 3 hydrogens, where up here we only had 2 with 3 hydrogens. So if you don't believe me, feel free to go through and add up all those hydrogens, and you will see all of them end up giving you the same number of hydrogens. All right, moving on then, let's talk briefly about alkenes and alkynes. So these are hydrocarbons, so just carbon and hydrogen is the only thing in the molecule, but these are now unsaturated hydrocarbons because there are now double in the case of alkenes and triple in the case of alkyne carbon bonds. So there are bonds between the carbon molecules that are not single bonds. And so because of that, not every possible bond that could be used for hydrogen is being used for hydrogen. There's essentially a bond, so to speak, wasted. And again, it's not, I'm just using that term to try and convey how the things were named. It's not actually a waste to have a carbon-carbon double bond. But that bond could have been used to bond to a hydrogen, or 2 hydrogens actually. And so that's why it's called an unsaturated. We have not used all the bonds possible to bond with hydrogen. So alkenes are named very similar to the alkanes. So if you remember, alkanes were called ethane, propane, butane, pentane, hexane. Alkenes, where we have double bonds, they have the same root names, except instead of ending in ane, it's going to end with ene. So we have ethene, propene, butene, pentene, and hexene. And we also have to specify where the double bond is in the molecule. So you notice here after propene, we start with 1 butene, 1 pentene, 1 hexene. That's just because we could theoretically have the double bond in the middle of the molecule as well. But up here with propene, whether we have the double bond here or whether we have the double bond here, it's still attached to the first carbon. Because again, if you say, well, no, it's not, because this is carbon number 1, well, that's just because we have it drawn that way. If you take that and you flip it, well, now this one's number 1. So you're always just going to number it so that the hexene, the ene portion there, has the smallest number. That's how we number those things. Which, by the way, I'm not going to have you naming stuff in this class. Just giving you information. The alkynes are very similar. So instead of ethene or ethane, we have ethyne. So, and once again, we have to specify which carbon the triple bond is attached to. So we have ethyne, propyne, 1-butyne, because we have that triple bond in the first one. It theoretically could have been between these two, which would have been 2-butyne. And I think that's also commonly called isobutane, but anyway. I'm going to call it 1-butyne, 1-pentyne, and 1-hexyne. Alright. Lastly here for this video, you can have molecules made of carbon that form ring structures. These ring structures are always called aromatic compounds. So if you have an aromatic compound in chemistry, you're not necessarily saying that because it smells. That is kind of the common use of the term aromatic. See, like, oh, yeah, some very aromatic flowers or some very aromatic air fresheners or something like that. You know, it's something that smells a lot. The term aromatic in carbon-based chemistry, in organic chemistry, specifically is referring to carbon compounds that have ring structures in them. That being said, carbon structures that have ring structures in them are smelly. They smell a lot. Sometimes good, sometimes bad. But they do also smell. That's actually where the term came from. But just because a carbon compound is smelly does not necessarily mean it has a ring structure in it. Most carbon compounds actually stink. But specifically, ring structures are called aromatic compounds. And any ring structure, it doesn't have to be just this 6-membered ring. Any ring structure is going to be called aromatic. And there are lots of different kinds of these ring structures, and different names that we apply to these different kinds of ring structures. So this would be called toluene, because we have a methyl group attached to a ring. This is aniline, phenol, styrene. You've probably heard of all those things, or at least maybe at some point heard of them, and it's bringing back memories of hearing those terms. But all these different things are just, in general, called aromatic compounds. Alright, I think we'll call it there for this video. In the next one, we'll start looking at some functional groups that you will find in a lot of different organic compounds.